Welcome to our Motivation for Sequential Design of Experiments video. I'll talk a little bit about why this is such a powerful approach when we're collecting data. Suppose you're booking an exotic tropical vacation and you're given two choices. You can either pay for everything right up front, or you can pay for a portion of a trip now and then closer to the event pay for the whole thing. I think almost all of us would choose option 2. There's more flexibility, and we know that things can change between now and when we go on our trip. And so the idea of sequential design of experiments is exactly the same. We want to collect data and spend our budget as we go, and as things change and as we're collecting data and we're learning things, we want to take advantage of that and adapt our strategy. So that's some of the motivation for why this is such a powerful approach. Here's a typical collection of steps that we often have, and you can see that each one of them has its own motivation. We might start with a pilot study where we're just trying to establish that we can get good quality data and measure everything that's needed. This typically isn't a formal designed experiment. Then we might do some exploration of the input space. We're trying to understand those basic relationships between the inputs and responses, and so we want to make sure that we have enough data to explore throughout the region to understand what's happening. And we might do that in more than one step. Once we have some basic understanding of those relationships, we want to build a model, and that's capturing those relationships into some format where we can make predictions from that model going forward for any new location. Again, this might be done in more than one step, collecting data, and then once we have a good model, refining it by putting new data points where we have maximum uncertainty for a prediction. Once we have confidence in that model, then we might use that model for optimization. So here we might have a focus region that is maximally interesting to us, and we want to put more design runs close to that because we want to understand that region as well as possible. And then lastly, once we know where our target destination is for running the process, we might run a confirmation experiment. And that's again a typically very small experiment where we're just trying to duplicate results that we've seen from our model. So let me illustrate that with a very simple example with two inputs. We're going to collect a total of 18 runs. In the first stage, we collect 2 pilot runs. This is just establishing that, in fact, we have the capability to collect the data that we want. In the second phase, we do exploration, and you can see that this is a space-filling design where we've put our 6 runs throughout the input space. And from that exploration, perhaps we discover that some region is not actually of interest. So either it's not viable for collecting data, or it just does not have desirable output or response values. From there, we might do model refinement. In this case, we've done another space-filling design, in this case targeting regions where there was large uncertainty. You can see that many of these runs are towards the outside of our input space region. From that refined model, we're able to identify a region that's of maximal interest, so that's the oval circle. So that's where we want to optimize our process. And so we run another small space-filling design inside of that region, and that gives us detailed information close to where the optimum is. And then finally a confirmation run, 2 runs quite close to where that optimum has been identified. So this gives a sequence of runs. You can see our total budget of 18 runs has now been spent, but we have good understanding of where the optimum lies, and also we've explored the entire space. I think it's helpful to make a comparison with what the experiment would have looked like if we'd committed all 18 runs at the start. On the right-hand side, we have a typical 18-run space-filling design for the entire region, and you can see that many more runs were allocated to that region in the top right corner that later became not of interest, so we wasted some resources there. and we have much less data close to where the optimum lies because we weren't able to update our thinking and target that region in subsequent stages. So, the keys to successfully implementing sequential design of experiments: we need to be able to collect data, model the results, model our understanding of results in a timely fashion. And so that being able to update in real time is a key component, because we're going to collect data and then update our knowledge and then act on that updated. We need to be able to articulate the purpose of the experiment. You could see as we move from pilot to exploration to model building and refinement to optimization and confirmation, each one of those had a separate goal, and we need to be able to translate that into what we're trying to do at each stage. And then the third one is where the FOQUS module actually is helpful. We're going to provide those tools for creating those designs that take into account data that we've already collected. We call that historical data. We can adapt it to different objectives, and then we have flexibility on the number of runs that you want to collect and also the region of interest. So we have tools to help with the third one, but the first two are key for the experiment to bring to the process. So the two primary tools that are included in FOQUS at this point are uniform space filling designs, and I've given a couple of examples here. The top example is we start with a regular region and we just want to do space filling. The second example is we have some historical data, perhaps from a previous stage, and we want to build a good uniform space filling design around that. And then the last one is we have an irregular region, and that can be accommodated as well. The second tool is non-uniform space filling designs, and so these are designs that provide the experimenter with good control to change the density of points to match their level of interest. On the right-hand side, you can see that the user has provided some contours. So think of the contours as at the peak of a mountain in the left bottom portion with the circle. And what we've done is we've taken those contours and translated them into a different density of points throughout the region. You can see that there's a higher density of points near the top of the mountain, and then we still have space filling as we move down the slopes of that mountain, but there's fewer points allocated there. And so that's a tool that we have possible. So a typical sequence of space filling designs: the pilot study, those orange dots, typically have no structured format. They're small enough that we just collect a couple of points to see what's going on. In the exploration phase, that's the blue circles, a uniform space filling design is typically used, and we have flexibility there for it either to be regular or irregular for the region that we're putting the points in, and with or without historical data. In the model building or refinement stage, we can use either the uniform or the non-uniform space filling designs that accommodate the historical data that we've captured in a previous phase. In the optimization phase, those are the green circles, we're typically looking at a smaller region, but then either a uniform or a non-uniform space filling design that incorporates historical data are a powerful way of tackling that. And finally, the confirmation design is typically just 1 to 3 runs, where we're making sure that things are as they seem in the model, and there's no structured design there. So you can see with the strategic use of the uniform and the non-uniform space filling designs, we have very flexible situations for being able to move through this sequence of steps and in fact create the design